when we are doing this type of transformations, essentially what we have done is we have transformed the coordinate system of E1, E2, E3 to a coordinate system E1C, E2C, E3C. So why is this really important? This first coordinate system is basically the coordinate system which is associated with the frame of reference of your sample, whereas the second coordinate system is the one which is associated with your crystal. Okay, so now if we are able to do this type of transformations properly, what we are essentially doing is we are first rotating about this E3 direction, just repeating what we did to ensure that E1 is going to coincide with E1 prime. So this was what we said was phi 1, and this was our rotation phi 1. The second rotation, as we said, is like this. This is a rotation of phi, and this is now going to generate an interim case where I already have the E3 axis for the crystal coming about like this. And then my third rotation is this R3. So here the idea is to perfectly align E1, E2, E3, which is the coordinate frame for the sample, with E1C, E2C and E3C, which is the coordinate frame of the crystal. And that we do by doing another rotation over here, so that you end up with this E1C and E2C. Okay. Now, once you have done this rotation, so if I now go ahead and write down the overall transformation matrix, then this overall transformation matrix is going to have components of all of these three rotations. So this can be written here as cos of phi 2, sine of phi 2, 0, minus sine of phi 2, cos of phi 2, 0, 0 and 1. Okay, so this corresponds to one rotation. Then the other rotation, which is about the E1 axis, so this rotation is about the E3 axis, this rotation is going to be about the E1 axis. So this becomes 1, 0, 0, this becomes 0 and 0. So essentially what's happening, when you are rotating about E3 axis, then you are pretty much taking the direction cosines associated with the E1 and E2 axis. So you have a cos phi sin phi and a minus sin phi cos phi. Everything else is 0, and the axis around which you are rotating, so this one over here becomes 1. So using the same logic, when I am rotating around the E1 axis, this position becomes 1, everything else is zeros, and then the direction cosines would be along the E2 axis and the E3 axis. So here I am going to have cos phi sin phi, then I'll have minus sin phi cos phi, which is pretty much along this. Now, as far as the third one is concerned, I would urge you to pause the video, recognize that the third rotation is around the E2 axis, and please go ahead and write that out yourself. Okay. Now, as we go through this discussion, one of the things I'll just highlight once again, that I have been using subscripts E1, E2, E3. So by default, that is basically describing the frame of reference which is associated with the sample, and wherever I have got C written over there, that's the frame of reference which is associated with the crystal. Now, at this point, it is pertinent if we point out some of the redundancies or the loss of uniqueness. One thing I will point out is when you are looking at this coordinate system, you can always rotate it either way, and so E1 can be mapped either to E1 prime or to minus E1 prime. That is fine. And so when you have phi equal to 0 or pi, then only your phi 1 plus phi 2 and phi 1 minus phi 2 are going to be defined uniquely. So this actually brings us to some of the limits that we can have of this Euler angles by which we are doing the rotations. So this Euler angles would be such that your phi 1 has to lie between 0 and 2 pi. Phi, which is the second rotation, that lies between 0 and pi, and then again the third rotation, phi 2, that is going to lie between 0 and 2 pi. So these are basically going to be the limits of your Euler angle. Now, once we have a little bit of an idea about the mathematical transformations which is needed to map the frame of reference of the sample to the frame of reference of the crystal, we can now move forward and actually start defining the function. Anytime you want to define a mathematical function which is representing the microstructure, you have to define the frames of reference very well within which you will be defining the microstructure function. So with that, we will now move on to this concept of the microstructure function. Now, having defined this basic concept of how the frame of reference of the sample can be mapped onto the frame of reference of a crystal, we now have a way in which we can think about the space that is being taken up by the microstructure. In order to define the microstructure properly in this space, we now have to define the mathematical function which we are going to call a microstructure function. As we move towards a microstructure function, our basic goal is to develop a function which takes the form of m, h, x and t. So essentially what this is saying is this microstructure function is going to be a function of your local states. The microstructure function is going to be a function of x, which is the position, and then we are also saying that it is going to be a function of t, which is the time. And building in the time aspect is important, because when you are looking at problems like grain growth or some sort of a phase transformation happening as a result of which the microstructure changes, many times these things are going to be time dependent. And therefore, when we define the microstructure function, we want to ensure that we are defining it in form of as a function of the local states, as a function of the spatial coordinates, as well as the function of time. Now, how do we actually think of a microstructure function? We think of the microstructure function as the probability density of finding a particular local state h at a certain location x at a certain instance of time t. So think of this like a probability density. That is an important part that we have to keep in mind. So what is it that we are doing over here? What we have done is we have just decided to think of the microstructural image as a probability function. In other words, what we are saying is, in case of real materials, the microstructure of two different regions, they don't have to be identical, but they can be similar. And this concept of similarity of two different regions of the microstructure arises due to the statistically similar probability distribution. If we are talking of microstructure function as a probability, then if you look at the microstructure function in two different parts of the material, statistically the distribution can be similar, but they don't have to be identical. And that is why when you are looking at a material and you're looking at different regions of the material, you get the feeling that you are looking at the very same microstructure, assuming of course that your overall material is fairly homogeneous. You get a feeling that you are looking at the exact same microstructure, even though the local microstructure at two different places are slightly different. So this thought that the microstructure function is essentially a probability density enables us to ensure that we can have similarity. So this is actually a fairly important part. Now, how do we digitally represent a microstructure function like this? Effectively, we need a digital representation because we will be doing some form of machine learning over here, right? So in order to do a digital representation of this microstructure functions, we start leveraging the concept of Fourier transforms. So how do we actually map a function? The idea behind mapping a function is that we probe a number of points in the space in which the function is defined, and then we start fitting the relation between those points in order to obtain the function. So the question is, how many points are we going to look at? And the short answer to that is more the merrier. One of the things we have to do in order to do this is we have to come up with a proper protocol for recovering functions using relatively small number of evaluations. So when you are trying to expand something in terms of Fourier series, as you know, you could have infinite coefficients, but we will not actually want to work with infinite number of coefficients. The entire idea that we are proceeding with is we have to be able to reconstruct the function given a fairly small number of values. And so for that we are going to use the Fourier transforms over here, and the Fourier transform means this function fx can be written as a sum of this fk times e to the power ikx. Essentially what we are doing is we are writing the function in the form of a Fourier series. So over here, what are this fk and k? This fk over here, these are the Fourier coefficients, and k is something which is essentially related to your periodicity. It is going to describe a cycle over which this microstructural periodicity seems to hold. So in that sense, you can think of k almost like a frequency. In fact, k over 2 pi is really what would be the frequency. And then once you are defining the function in terms of a Fourier series, you will need to find the Fourier coefficients, and using your standard definition, your Fourier coefficient is going to be given by the expression over here. Now, when we practically work with problems, we tend to discretize the space, and instead of using this type of continuous Fourier functions, what we will want to do is we'll want to find a way in which we can get into using discrete Fourier transforms. And so what we are doing when we are dealing with discrete Fourier transforms, we are starting with a set of function values which I am going to sample fairly uniformly from the domain of interest. So the domain of interest here is the entire space over which the microstructure is being defined. Now, once we do this, the advantage that we are getting is we are already starting with a fairly finite number of discrete evaluations of the function. The function has different values in different places. Since we are sampling different points from a fixed set and we are sampling only a fixed number of points, we are starting with a finite number of values of the functions defined over that space. Now, as we do that, we can also appreciate that this Fourier coefficient can now be written in form of a summation instead of writing it out in form of an integral. And once you write out the Fourier coefficient in form of a summation, you can also find the inverse Fourier transform once you know this expression, and so your inverse Fourier transformation is going to be given by this particular expression over here. Now, one of the things I would want you to note is that as we define this thing out, there is really no dependence on x. In other words, if you think in terms of dividing the microstructure into small bins, the size of the bin is really not going to matter too much as long as we have this type of a function. Now, the domain space for the microstructure function at any given time is going to be given by m, h, x and t. H over here is the local state space, and then this term x, that is what is going to describe your physical space, which is divided into individual bins. So in this case, what we have done is we have divided the space into n bins. Now after that, we start defining another term over here, MSN, and this is basically the volume fraction of the states S inside the bin numbered as n. All right. And so since over all of this bins, the total phase fraction over all of the bins is going to be 1, you will have this summation relation hold, that when you are summing over MSN starting from n is equal to 1 to n, that value is going to be 1, and therefore individually you have this relation that MSN lies between 0 and 1. So with this brief mathematical background, now let us actually see how we can start doing a fairly simple-minded representation of a microstructure. So if you look at the figure over here, the white and the gray, they are representing different phases. Now, when you look at the microstructure, features might seem to vary fairly continuously, but when we do a binary representation like this, given the pixelated form of a representation, you will find that this does not look quite as smooth. So what this really does is this white color represents whatever phase is present right at the center of this white cell. This gray color represent whatever phase that is present at the center of the gray scale, gray cell. And so what we basically start doing is we start reducing the microstructure into a set of whites and blacks or whites and grays. Keep in mind that the reason we are using the center of the cell to represent the entire cell is because we have been doing a discrete sampling in our microstructure space. All right. So if a state is represented in white, let us say by the number 1, and then the gray is represented by the number 2, if you look at this very small matrix which apparently describes a microstructure, you can actually start writing those MNS type of things over here. So in this case, if I look at M1 in the cell 1, 2, so the value of that is going to be 1 over 16. Similarly, if you look at M2 in the cell 1 over 2, the value of that is going to be 0. As you go forward, you can do the same thing, write the value of M1 over the cell 2, 1, and you will again find that the value is 0. And then after that, if you write M2 at 2, 1, you will find that the value is 1 over 16. So how are we actually getting to this value? So what we are doing, we are locating here the cell 1, 2. So that is basically the cell over here. And what we have said is that if the state is represented in white, it is denoted as 1. So I am talking about the state which is represented as 1, that is the white cell. Now if you look at this entire matrix, this is a 4 by 4 matrix, so you have got 16 possible states. And so the fact that you've got a white state over here, it basically means that this value is. Similarly, if I now do the same evaluation for state 2, which is the gray state, we find that over here you do not have any gray states, so the value is basically 0 over 16. So if you look at this other cell 2, 1, when we are looking at the value of the microstructure function for state 1, since this state is a gray state and we are looking at the microstructure function for the white state, or the probability for the white state, the value is going to be 0 over 16. However, when we do the same thing for state 2, which is the gray state, the value is going to be 1 over 16. So now what we had basically said is the sum of all of this microstructure function is going to give us 1. So if you start computing how many white states you've got 1, 2, 3, 4, 5, 6, 7 and 8 white states. So that means there will be 8 cells in which the probability distribution is going to come as 1 over 16. So what that basically means is, for the white cells, your sum of this probability or sum of the microstructure function is going to be half. So since you have got 8 white cells out of a total of 16, the number of gray cells is also going to be 8, and therefore the sum of probabilities for all of the gray cells is also going to be 8 times 1 over 16, so that is half, and therefore the sum of this entire microstructure function is going to be half plus half. In other words, it is going to be 1. So when one starts encountering a material system which has got a finite discrete local states, the local state at each of this sampling point is assigned to 1 and only one of the allowed local states. So that is something you have to keep in mind when you are trying to compute the values of M at the different cells. So once you have this type of discretized microstructures, we call them eigen microstructures. So hopefully this is now going to provide us with a reasonably good background as to how we can start thinking in terms of a microstructure function. Just to recap, this microstructure function is going to be a function of the local state. It is going to be a function of the spatial location, and it is going to be a function of time. And then what we said is this microstructure function is essentially a probability distribution. Probability of what? It is the probability of finding a local state h at a given location of the microstructure given by x in a certain point of time given by t. Since this is a probability distribution function, we further said that this sum of this probability distribution function summed over all of the states that we are looking at is going to be 1. All right. So there is a certain possibility that this state can occur in any of those 16 cells, and therefore, since this is only one case in which this we are finding the white cell, so when we are computing M1 for this case, it would be 2, 3. It is one case out of 16. So this is how we start evaluating the values of the microstructure function for different local states. So with this basic understanding, as we move forward, we will now start combining this with our concepts of the Fourier transformations in order to start developing spectral definitions or spectral descriptions of the microstructure. That is something that we are going to take up in the next lecture. Once again, thank you very much.